Hello everybody, how are you? Welcome to our channel Turbo Electronics Education. In today's lecture, we are going to show you how a PCM, that is a Pulse Code Modulation, is being performed in the laboratory. Basically again, just like our previous videos, I am not going to show you detailed PCM expression and analytical expression and its analysis and every other things, but I am just going to show you how we will perform PCM in laboratory, and for that we just know some knowledge, we must have some knowledge. So for that knowledge, just I am going to making this video. Please listen to this video carefully. This video may be a little bit long, but if you listen this video from first to last, you will be very much benefited, because from basics to advanced I am just covering all the things of PCM without any analytical equations. So this lesson here is going to be very much easy. Just listen. So without wasting any more time, let's start our video. Listen. These are the course outcomes that we will study during studying the PCM actually. So first of all, we will know what is a continuous time signal and what is a discrete time signal, and how to convert the continuous time signal to discrete time signals. That's nothing but the sampling. Basically the 3 and 4, these topics are quite much similar. Basically sampling is the answer of this question. What is the how to convert the continuous time signal to a discrete time signal. Okay, now we will see the quantization, then we will see PCM generation, how PCM is, that is the pulse code modulation PCM code is how generated, that we will see. Then we will see the block diagram and operation, and we will also see the key modulation and demodulation. And also along with it, I will show you through a short video how this PCM is measured in the lab. How to measure the PCM codes, how to detect, how to recognize the PCM codes. Okay, and I will also show you the other diagrams that is quite related with the trainer kit also. During performing the experiment, we will see several types of waveforms in the DSO. I will just show you the pictures of these waveforms in this video, so that if you perform this experiment in the laboratory, you won't face any kinds of problem, any kinds of trouble. Okay, so let us start our first topic, that is continuous time signal. Basically, what is the continuous signal? That is nothing but the continuous time signal. So our first topic is continuous time signal. If I tell you the definition is like the signal that is continuous in time and continuous in amplitude. Okay, continuous in time, continuous in time and amplitude is known as the continuous time signal. The signal, those signals which are continuous in time and continuous in amplitude. Let me draw a demo signal. Our sinusoidal signal, that is also a continuous signal, but I am just drawing is this signal. This is a 0 point, this is time axis. If you can see that this signal is continuous in time and continuous in amplitude. How we can detect it? Because any 2 points, if you pick any 2 points in the time axis, that is time t equal to 5 and t equal to 6, in between them, if the distance of the points is very small or very large, whatever, if you pick the 2 random points on the time axis, and if you can measure the value of this signal at that times, then you will see that the values are different. That means its value is continuously changing with respect to time. Its value is not fixed. So that's why we can tell that this signal is continuous in amplitude. And it is continuous in time. Why it is continuous in time? Because the difference of the two instant, that is the del t, if you can pick the two instances, for example two instances time domain which are very small, their difference is very small. If you can pick this type of time instances, then you will see if this difference is tends to 0, for then also the values of the amplitudes are not same. Okay, that means for small and smaller differences you will find the different values of this signal. That is xt is a continuous time signal. From here we can say it. So that's why we can say it is continuous in amplitude for at any two instances of the time, or at any two instances of the independent variable with respect to which we are measuring the amplitude of this signal. Okay, that means we can't find a fixed amplitude in between two time intervals. Okay, that's why it is called a continuous time signal. So let me show you the discrete time signal, then it will be more clear to you. Discrete signal. Discrete time signals are those signals that are sampled in time and quantized in amplitude. The term sampled and quantized, these two terms will be clear to all of you later, but for now I am just drawing and I am just writing the definition, and I am just drawing these signals in the discrete domain. Then the signal looks like the discrete domain, it is represented by n, not in t. So the signal in discrete domain will looks like just like this. That means what are we doing actually? We can find the values of this signal in discrete instances. This is 0, 1, 2, 3, 4, 5, 6. We can find the value of the signal at 0th instant, 1 instant, 2nd instant, 3rd instant, etc, etc. And not only that, we will find a finite value. That means for 0th instant the signal has a particular value, but for here, for this case, for the previous case at 0th instant, we can't say that this signal has a particular value because its value is continuously changing. But here the value is discretized. That means as we are finding each and every instant values, these values are called the quantized value. Okay, for now just understand this. I will tell you later what is a quantization and what is quantized values. But for now, if you are seeing that there are number of discrete values here at discrete time interval. That means in each and every time interval of the discrete domain, we can find a particular value of this signal, and that value is called the quantized value. And not only that, you can see that the time domain has been discretized. That means time domain is not continuous. For here for example we can say that 0, 1, 2, 3, 4, these are the discrete times. That means in between 0 and 1s, no time, though no time samples has been taken, no time has been considered. That means for after 0th time, 1th time has been considered. This is called the sampling or the sample. I will tell you sampling later on. But for now, just understand that the time domain is not continuous. That means the zero in between 0 and 1 there is no other values has been considered. So that's why this is called the discrete time or the sampled time. Okay, so that's the nomenclature, that's the notation that I want to tell you. So two things has been happen here, that is one is quantized amplitude and second one is sampled or discrete time. Discrete time means the time has been discretized and we have taken some particular time intervals. Here we haven't taken some particular time interval because the time is always continuous. And not only that, for each and every time interval we have mentioned some amplitudes, we have defined some amplitudes of this signal, and this signal is denoted by x of n because n is for discrete signal. Okay, and x of t, that is t, is for continuous time domain signal. So this is the basic difference. Now the question that generally arises, that is the basic funda of our topic, that is how to convert this continuous time signal to discrete time signal. The answer is sampling. That is 3 plus 4. We are converging, we are merging two topics together. That is sampling. Our main focus is how to sample a signal. This is the main vital topic of today's lesson. Because if you don't know sampling, you can't do quantization, and if you don't do quantization, you can't determine values. If you can't determine values, then you won't be able to generate the PCM. Okay, so each and every stage, this is the 4, 5 and 6, these three steps are very very important for our lesson, because these three steps are interlinked with each other. And the block diagram is also important, but if you understand these three steps, this block diagram will be very very easy. So just listen to these steps carefully. First of all, sampling. Now why are we doing sampling? Because we are converting the continuous time signal, CT signal, to discrete time signal. Okay, our motto is that. Why? Because we are studying digital modulation. Anything in our nature, our voice, it's our mobile phone signals, etc., etc. Okay, all the signals, even noise, etc., are continuous in nature. But as we are studying the digital communication, so that's why we must have to communicate from sender, in between sender to receiver, in digital domain. That means we will transmit the digital signals, not the analog signal itself. Our analog communication was over in third semester. So there we have seen that we are sending the analog signal, but if you notice carefully, each and every analog signals must face a common difficulty, that is noise. And for removal the noise, we have just jumped into the digital signal, and that's why we are in today's world, we are doing each and every communication in the digital domain. That is called the digital communication. Now to perform the digital communication, we must have to know how to convert our continuous time signal, that is the natural signal, into the discrete time or the digital signals, right? If you can convert the continuous time signal into the discrete time signal, or from discrete time signal to the digital signal, then we will be able to transmit those digital signals. This carries the information actually of the main message signal. Okay, that means the main information of the message signal has been converted to some bits or some digital data, and we will transmit those digital data via wires or wirelessly from transmitter to receiver. So that's our main motto. So that's why we are studying how to convert the CTFT, the continuous time signal, to the discrete time signal. Now, continuous time to signal to the discrete time signal, we will do sampling. Now, how to do sampling? Let us see it pictorially. This is a continuous time signal. Okay, that is xt. We will do what? We will just multiply this continuous time signal with an impulse train. We know the impulse train. Okay, this is not a single impulse, there are multiple number of impulses present here. Okay, and this, and value of each and every instant, and we have taken here that the impulse train is in discrete domain. That means, what is the property of this impulse here? The property of this impulse I am again writing, though you all know, that is del n equal to 1 for n equal to 0. Okay, for n not equal to 0, del n equal to 0. In discrete domain, the property, the impulse train, the impulse signal basically is recognized by this. This is the impulse signal. That means the signal has only value, that is 1, a single value, that is 1, at n equal to 0 point. That is the 0 point. That means the signal has only the value at n equal to 0 point, that is 1, and at other position the signal has no value. You can see the other position, the signal has no value, that is the 0, but at 0 position, n equal to 0 position, the signal has a value, that is 1. Now this is there is not a this is we are talking about a single impulse, but you can see that there is not a single impulse, there are multiple number of impulses. Now how to write this impulse train? There is impulse train, we can say, listen to the words carefully. For single impulse, we were saying that the del n, and we know that at n equal to 0, the value of del n is 1, right? Now for impulse train, we can say that the same impulse has been shifted to the right as well as the shifted to the right. Right? This same impulse, this is the same impulse, is present at the 0 also, and as well as this impulse has been shifted to the right as well as it has been shifted to the left. So what we can write, that is, we can write a same impulse that is also present at 0, and we can shift this impulse to the right, that is n minus 1, n minus 2, n minus 3, and this is continuously shifted to the right. This impulse is continuous in right direction, as well as this impulse is continuous in left direction also, because this is an impulse train, this is not finite, right? So for left shift, what we can apply? We can apply del n plus 1, del n plus 2, and so on. So that means we can write our impulse train as a shifted impulses, as a number of shifted impulses, right? We can write our impulse train something like that. If we can write our impulse train as a number of shifted impulses, then we can say that the single impulse has been repeated again and again, and this has formed a impulse train, right? This is quite easy, because why? This impulse has been present at 1 position, 2 position, 3 position, 4 position, and so on in right side, and also present is minus 1 position, minus 2 position, minus 3 position, minus 4 position, and so on and left side. Okay, so I think this point has been clear to you. So now the main important thing, arises. What is that? Property of an impulse. Property of impulse. See, impulse has a very beautiful property. Suppose that you are multiplying a signal xt with a impulse. Listen to this word carefully. Suppose the signal is like this, and a single impulse can be written how? That is, at 0 it has the value 1, and for other position of the n the impulse has no value. Now if you can see here, at 0 the impulse has only one value, that is 1. If you can multiply these two signals, though one is a time domain and one is a discrete time domain, whatever, but just to multiply the position wise these two signals, what will happen? For this signal, without the position of 0, other position of the left side of this 0 as well as the right side of this 0 will be multiplied by the 0 of the impulse. I am making it more clear. That is, see, this signal is being multiplied with this signal. So how to multiply two signals? That point by point, that is 1, 2, minus 1, minus 2, whatever. We will multiply minus 2's position with minus 2 position of this impulse, minus 1 position with the minus 1 position of this impulse, 0 position with the 0 position of this impulse, and so on. So as we are going to do multiply with this signal to this signal, we can see that the impulse has only value, that is 1, and that is present only at n equal to 0. So without n equal to 0, without the position of n equal to 0, the impulse has no value. As this impulse has no value, that means we can assume that no value means what? No value means that impulse has the 0 values, that I have also written over here. That means the impulse has 0 values. So without position at n equal to 0, the impulse has 0 values, and these 0 values will be multiplied with the finite values of the xt signal that is not present at n equal to 0. That means without the value at n equal to 0, all the other values of the xt signal will get multiplied to the 0, because the impulse has 0 values without the position at n equal to 0, right? Now 0 multiplied with 0 something, or multiplied with something, that will make 0, right? So now what will be the output? The output will be, there must be a signal, and left portion of this signal, the left portion of this output will be 0, as 0 is multiplied with finite value, that is 0, and right portion of this signal, that is 0, is multiplied with the finite values, that is also 0. But what will be at position 0? At position 0, you can see the 1 is being multiplied with some values present at t equal to 0 of this signal xt, right? You know, suppose if the value is a, so a is being multiplied, a means the value of a means at t equal to 0, suppose the value of the signal is a. So what will be the result? That means the a will be multiplied with 1, that means the value of a will appear here, right? So now what is this? This is actually x of n. X of n means at n equal to 0, you will find the result only, that is nothing but the same amplitude present that was present in the same signal when it was a time domain, okay, and the other values of the signal will be 0. That means we can conclude this point such a way that if we multiply an impulse with some continuous time signal, the result will be the value of that signal, at that position where the impulse was present. See, as the impulse is present at 0th position, that's why we have found the value of the xt signal at a equal to 0, that is nothing but a. Assume that if the impulse is at 1 position, that means at 1 position the impulse has only the value 1, and for other positions of n the impulse has value 0. So what will happen? Just like in previous way, we will find the value of this signal at 1 position only. We will find the value of the signal at 1 position only. This is the beautiful property of this impulse. Okay, so if we write it in the equation, then we will found that if the xt signal is multiplied with del n, then xn will appear, right? If the xt signal is being multiplied, then del n minus n naught. What is n minus n naught? That is, the impulse train has been shifted n naught amount of time. Here impulsion has been shifted one amount of time, then you can say that this is nothing, sorry, not this. This is nothing but this impulse has been shifted one amount of time, so you can say that this is nothing but n minus 1. Okay, so just like as we have written the n minus n naught, that means impulse train has been shifted rightwards by n naught, that is impulse is present at n naught. Then what we will get? We will get x of n naught. Okay, again if the impulse train has been shifted to the left side, that is n plus n naught, then we will get x of minus n naught. That means that n has been shifted to the left side. If this is clear to you, that means whatever we are concluding that wherever the impulse is present, if that impulse is multiplied with any continuous time signal, we will find the value of that continuous time signal at that position where the impulse was present. That is, the location of the impulse where it was present will be multiplied, the value of this impulse, that is 1, will be multiplied with the total signals, and the value of that continuous time signal will be just the same value, but the value will be found at the position where the impulse was present. Okay, this is a very simple phenomena. I think you have understood this. If you can understood this, then you can tell this result very easily. How? See, we are converting a continuous time signal in a discrete time signal by means of impulses. So that's why we have also written over here a xt signal will be converted to the xn signal, that is the continuous time signal will be converted to the discrete time signal if we can multiply the impulse train, that is the discrete impulse train. Okay, very easy. Now tell me the output. What will be the output? Very much easy, very easy. The position, if you can see that there are multiple number of impulses, right? And there are some, for each and every impulse there is a particular position. Suppose this impulse is present at -4. So -4 only, at -4 only the value of this signal will be found. Okay, because I have already told where the impulse is present, at that position the value of the signal will be the output when that signal will be multiplied a single impulse or a impulse train, whatever. Okay, so for this impulse I have found this value. This value is nothing but the value of xt at t equal to -4. Similarly for -3 we will found some value, -2 also will be found some value, -1 also will be found some value, and in similar way we will find the value of the same signal but in discrete domain. As the impulses are present in the discrete time intervals, so that's why the value of the signal will be in discrete time domain also, right? So you can see that we have discretized the continuous time signal in the discrete time signal just by multiplying a simple impulse train. This is nothing but sampling. That means we have sampled, again listen to my words carefully. We have sampled this continuous time signal at some values. What are the values? The values are -3, -2, -1, 0, 1, 2, 3, 4, whatever, etc., etc. At that particular times only we have sampled. That means we have just taken the sample of this value. We have just taken some samples of these signals at that particular points or at that particular times, and just plotted the values of the signal here. Okay, that means mathematically we have also shown you, that is, we have just multiplied the continuous time signal with the impulse train, and we have found the discrete time signal at the same positions where the impulse is present. Okay, now there is a problem. What is the problem? Now I will discuss the problems about sampling. Problem. Now we will see what are the problems. Problem is the impulse. Actually, you know that the impulse doesn't have any existence in the real world. That means we can't say that such a signal that is first of all present at t equal to 0, at t equal to 0 can't be measured in any type of instrument in the real world. So we can't say that at t equal to 0 the value of this signal is this. We can't say, because t equal to 0 time we can't measure, first of all. And second thing is, at t equal to 0, if we consider the continuous time impulse, then we know that at t equal to 0 the dt, that is the continuous time impulse, that is the del t, the value of del t is infinite. Okay, that means del t is, value of del t is infinite at t equal to 0 and equal to 0 at when t not equal to 0. Okay, that means at t equal to 0 we can't find such a signal in real world whose value is infinite, because first of all that infinite thing cannot be measured, and second thing we can measure at t equal to 0 time also. So that's why this impulse that I have shown over the previous slide, or in the previous page, that cannot be existent in the real world. Okay, one more thing that I want to mention, that is this del t signal, that is the delta t signal, that is the impulse signal, is in time domain. Okay, but if there is the continuous time domain, but in discrete time domain the del n value is 1. No confusion about it should be remain. Okay, at n equal to 0 in discrete domain the value of the impulse should be 1, but at time domain the value of the impulse should be infinite. But at t not equal to 0, that is without the 0th time, in continuous domain or in discrete domain, whatever, the value will be always 0. And one more thing, that is that most of the students may have confusions. At t equal to 0 the value of the impulse is infinite, but if we integrate the impulse signal at time domain, okay, for minus infinite to plus infinite, then that value will be 1. That means the area under the impulse signals, area under impulse What is that? Equal to 1. Unity. Okay. Area under the impulse is unity. Remember it. This thing is completely different. Time domain and in continuous time domain and in discrete time domain, the nature of the impulse is completely different. Just remember it. Okay. So, how to recover this problem? So we can't generate the impulses in time domain, but we can generate a square wave or the pulse of very small width. Okay, this is possible, right? Because this pulse has some finite duration as well as some finite values. Okay, though the duration is very small, but whatever, there is a finite duration and as well as it has a finite values. Okay, so that is the pn can be generated. This thing can be generated. This cannot be generated, but this is possible. Now we can say this thing is not also possible that we were doing in the previous case. That means as in previous, what we are doing actually, we are just multiplying a continuous time signal, that is xt, with an impulse train. But what we will do now, as impulse train is not possible to generate, we can generate a small width of pulse train. This is this. You can generate this, right? We have no problem about it. You can generate this. And for this, a little change will be done over here. What will be the result? A little change, not a very drastical amount of change. A little change will be done over here. That is, we will find this value like as this. I think you can understand what I am trying to do. That means, as there was an impulse train, there was a single lines. There were multiple number of single lines. As there was an impulse train, right? As there is a square, this is a single square. For a single square, the value has been sampled for this finite duration. Throughout this small finite duration, this value has been sampled. So throughout this small finite duration, what was the value that will be here? Then here is a problem also. Okay, I think this portion has been understood. As these pulses have some finite durations, so that's why for some finite durations only the signal will give some values. That means at the previous case we were finding these signals in discrete domain just by a single line, that means multiple number of single lines. But here we will find some pulses, some mini pulses of very small widths. Okay, why? Because the impulse train, that is not actually the theoretical, that it is the practical impulse train has been multiplied with it, and this practical impulse train have some finite durations. So that's why we will find some finite durations in the discretized exchange. Okay, now there is a problem again. What is the problem? Problem is, see, as this signal is continuous in amplitude, the top of this sample will be not like this. What will be this? This will be like, for first impulse, this will give this. For second impulse, then for third impulse, fourth, fifth, sixth, seventh, eighth. That means for each and every impulse train you will get these types of values. I think this is not too much clear to you. Now it will be very more clear. See, the top of the pulses, this is actually, we are assuming that the value of the magnitude of the pulses is 1. That means the 1 value will be multiplied also the magnitude of this xt signal, right? This 1 value will be multiplied with something, that is the value of the xt signal, will give the same value. If this value is a into 1, that will be a, b into 1 will be b. So that's why the pulses will appear like this. Okay, that means you can see though the signal has been discretized in time domain, that is we have found some values of the signal in discrete time intervals, but the magnitude of the signal is still continuous within these small time intervals. Within these small time intervals, that is a simple bit interval or single impulse interval, the magnitude is continuously varying. So this will create problem in quantization, because we will see that for quantization we need some fixed value, that is the fixed valued pulses. So as this will create some problem in quantization, so that's why we can't use it in the quantization, because we have already told you in the preliminary lecture when we are discussing the topics, after sampling our main aim is to do its quantization, because we have just sampled the signal, and from sampling we need to do quantization to get the discrete values or the digital values or the digital signals. So for that we need actually the fixed value of fixed valued pulses. We will later discuss why the fixed valued pulses are required when we will discuss the quantization. So for now, just know about that these continuous valued pulses will create some problem in the quantization, so that's why we can't use it. So this is again a problem, so that's why this cannot be used. What is used here? If we can convert this signal to this, that is this signal. Now you can see that the pulses has been taken, that the samples has been taken in discrete time domain, or that means the particular domain, particular time intervals, the samples has been taken, as well as the top of the pulses, top of the samples is flat. Okay, now this can be used in quantizer. This thing can be used in quantizer, and we can also say that this thing is continuous in time, discrete in time, as well as discrete in amplitude also. So this thing can be used in quantizer, we don't need to worry about it. But the two problems that was previous, this first problem was what? The two problems has been solved actually at the third position here. So what are the two problems I am discussing again? That is, first of all, we have seen over there that if any signal is multiplied by the impulse train, then we will find the same signal at that point, that time intervals where the impulse is present. And this was very good actually. This is the actually the best or the ideal case. But in practical we can't generate the impulse train. What we can generate? We can generate some pulse train, right? So we can generate some pulse train. if we can multiply the same pulse train with the continuous valued signal, we will find this type of signal actually. Not the actually this is this actually this is our desired. Okay, now don't look at this. Actually this type of signal will appear if we directly multiply the pulse train. It is not impulse train, it is the pulse train. That's why P of it is written over here. The pulse train is multiplied with the our continuous time signal. Then we will find this type of discretized xt signal. Okay, discretized xt signal. Though this value of the width of these pulses is very small, but we will see within this and the small width the amplitude is varying. Though this width is very small, it can be negligible, but whatever, for more accuracy, we can tell that within that small time interval, our amplitude is continuously varying. So this can create problem in quantizer. So that's why in quantizer what we need, we have to convert this to this. Okay, now coming to the point, when the one more thing, how to convert this to this. Actually for this we will use a circuit that is sample and hold. Up to now we were just sampling. Now not only here we will not only just sampling, we will also hold it. That means after sampling here this pulse will hold the value of the same of this signal that it was sampled in the previous. That means after sampling here, right, this value will be retained, this value will not be changed, this value will be retained same for that bit interval. Again for the next sample is taken here, the value will be same for throughout this small interval. That's why it is called the sample and hold. That is, it is sampling as well as holding the value that it has been sampled. That means the value isn't changing, right? So that's why the circuit that is used to convert these samples are called actually the flat top samples. To convert to perform the flat top sampling, we need the sample and hold circuit. So from here we have also understood there are three types of sampling can happen. One is impulse sampling. Here impulse train is used, right? This sampling is also called the ideal sampling. Why? Because this has not any existence. This is not possible in real world. This is possible ideally only. That I have shown here. Okay, this is the impulse sampling. Then we have seen the natural sampling. Natural sampling is this: we have just sampled the signal with the small weed pulses, but the problem is, what is the problem? Problem is the continuous has remained the amplitude has remained continuous in this time interval. So that's why it is called the natural valued samples. Then we have seen the best samples for that we can use in our quantizer, that is the flat top sampling. It is the best sampling technique that is used in our quantizer, that is this. And for this we need the sample and hold circuit. This sample is only possible for sample and hold circuit. So this is the flat top sampling that we will use across this session. Now sampling is done. Our fifth thing is quantization. This is very easy. Now whatever we have seen over here, we have just sampled this was a continuous time signal, okay, and this has been sampled to this actually. Now actually we can say we can see here that there is a small gap between these two. If we can consider this gap is negligible, this gap is tends to 0, then these pulses will be just attached with each other, right? This pulse will be attached to each other, and this pulse will be attached to this, and we can say that this waveform will be like this, right? You can see here that the pulses has been attached with each other. That means we are assumed that there is a negligible amount of negligible amount of width, negligible amount of gap between two pulses. This is our sample signal, right? But we haven't converted it in the digital signals, because we know that for digital signals, what is the digital signal? That is nothing but combination of zeros and ones. That means digital data is required. But here, from here, can we say that it is a digital data? No, because we can just only say there is a certain amount of discrete amplitudes only. Suppose this is 2 volt, this is 4 volt, this is 6 volt, this is 4 volt, this is 2 volt, this is 1 volt, this is about 0 volt, etc, etc. These types of amplitudes has been present, but these amplitudes are not the combinations of zeros and ones. For digital signal, we need the combination of zeros and ones. So for that we are doing quantization. What we are doing actually, I am drawing the same signal again. See what we are doing. Suppose I have found these signals after sampling, okay, and there are, we can say that there are number of varying amplitudes, not the varying, discrete amplitudes, discrete and different valued amplitudes, okay. So from here we have to convert digital data, that is the series of zeros and ones. That means we can generally see, we can, from our normal idea, from our general knowledge, we can say that for each and every amplitudes, right, each and every amplitudes, we need some digital data, right? For each and every amplitudes we need some digital data, then it will be very much easy, okay. As for each and every amplitudes we need some digital data, so for from that we can say that for each and every amplitudes we must have to assign some digital values, okay. So this is nothing but quantization. Quantization is nothing but we are just converting our sample signal, okay, that is the sample signal to digital data. If we can convert the sample signal to digital data, this is nothing but the quantization. Now how we can convert? The quantizer is the thing that can convert the digital data, that is the from sample signal to digital data. Okay, now quantizer can be any bits, that means for n bit quantizer can generate n number of combinations. Sorry, 2 to the power n number of combinations. That means if we can consider there is a 3-bit quantizer, 3-bit quantizer can generate 2 to the power 3, that is the 8 number of combinations. Okay, 8 number of combinations of data. Now how this is assigned in with these amplitudes? Suppose we are assuming that we are using the 3-bit quantizer, and from this 3-bit quantizer we can see how many combinations of data, that is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. 3-bit quantizer means these are the 3 bits, and these are the 8 possible combinations that we can get. Again I am telling, if we are using the 3-bit quantizer, then we can see that for 3-bit quantizer we can get 8 number of combinations, and we have to put this 8 number of combinations to the discretized amplitudes. To these discrete amplitudes we have to assign this 8 number of combinations. Now how to assign it? Suppose this is 0, 0, 0. This is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so that means actually for this amplitude, for this value, we can get the digital data 101. For this value we can get the data 110. For this value we can get the data 111. Similarly, like I have not actually declared the particular positions at the exact positions of these data, of these digital values. Okay, so don't think that what will be the value, what will be the digitized value, what is the quantized value for this amplitude. So don't think that, because I have not drawn the diagram perfectly. I am just giving you the example, giving you the process how this is generated. So this is nothing but the quantized value. That means what is value is giving these values, the combinations of these values are giving the actually the digital code, the digital data. That means you know the signal is varying from these to these. Now what will be the code for this? What will be the code for these? Suppose the signal is started varying from here, and here it is going this. For this 101, then it will jump over here, that is 110, then it will be 111. Similarly, like when it will drop, suppose from here, what it will be, it is just similar to the 100, 100. After that this is 010, this is 001, this is 000, again this is 001, this is what 0 1 0, and in this way you can see that a continuous value, for a continuous valued signal we have discretized this continuous value signal in the discrete domain. We have sampled this signal, and from this sampled signal we are getting a continuous code, right? As that as the signal, as the continuous time signal is varying in time, similarly the discrete or the sample signal is also varying in time, and as the sample signal is varying in time, the combinations of the values or combination of the quantized values are being changed continuously, and due to changing of this continuous combination of the quantized values, we are getting multiple number of 3-bit combinations for a 3-bit quantizer. For a 4-bit quantizer, we will get 4-bit combinations, and obviously for 4-bit quantizers, as we will get the 18, we will get 16 combinations. So that's why there will be the 16 number of datas. That means we can get the 16 different, we can map the 16 different values of a signal. Here we can map only the 8 different values of this sampled signal, okay, of this flat top sampled signal. But there, if we use the 4-bit quantizer, then it's 2 to the power 4, that is 16 number of combinations will be there, and we can map the 16 different values, up to the 16 different values of the flat top sampled signal. Okay, here we can map only 8 different values. So whatever, we can see that for each and every different values we are getting some 3-bit codes for 3-bit quantizers, right? Similarly, if this value is varying continuously, if the signal is varying, obviously the value will be varying from this, and this value is varying, and for that we are getting several combinations of the 3-bit codes. That is, first of all we are getting 101, then 110, 111, 110, 101, 100, 011, and similarly like 01, 001, 001, then 010, 011, 100, and in this way we are getting the continuous combinations, continuous 3 combinations, and we can say actually what we are getting the binary codes. What is the binary code? This is the number of ones and zeros, and within the number 3 combinations are present consecutively. That is defining the several amplitudes. That amplitudes are nothing but these discretized amplitudes. Okay, so as the 3 combinations are transmitting, 6 combinations are generating serially, and for that reason we can say that the output, that the bit pattern that we are getting is continuous ones and zeros with several combinations of ones and zeros only, and this is nothing but our PCM code. Why PCM? This code that has been generated after the quantized value, that is nothing but the PCM code. Now the question arises, the why PCM? If we write the word PCM elaborately, that is the Pulse Code Modulation, right? Pulse, what is pulse? This is the sampled and whole signal gives. Okay, from sampled and whole signals, basically we are getting this pulse, so that's why it is called the pulse. And code we are getting from quantizer and encoder. Encoder is nothing but we have quantized, that means we have make the 8 combinations, and for this 8 combinations, encoder is nothing but just picking the particular combinations for a particular value, particular what can I say, that is particular magnitude. For a particular magnitude, encoder is assigning a particular combination. Okay, quantizer is nothing but 3-bit quantizer means it is making the 8 combination. It is dividing the total signals into 8 different amplitudes. That means it can say that you can divide the total signals into maximum 8 number of amplitudes for a 3-bit quantizer. For a 4-bit quantizer, you can divide the sampled and hold sampled signal into 16 number of amplitudes maximum, and from the 16 number of amplitudes, encoder is doing a task that is nothing but it is just assigning the values of the amplitudes to a corresponding 3-bit or 4-bit whatever an n-bit code. Okay, that is the quantizer and encoder. We will see in the block diagram. So quantizer and encoder gives the code, and modulation is just to, we cannot transmit actually the digital bits because in physical channel we cannot transmit the digital bits. What we can transmit? We can transmit something like this, some kinds of analogous bits, but we can't transmit actually the pure digital bits through the channel. So we can transmit these analogous bits, and these analog bits are generated by this modulation. We also know, we generally know what is modulation is, because we can now transmit our baseband signal, and for that we need a high frequency signal, that is the carrier signal. Each and every story we know, and I am not giving details about it. But what we are doing here, actually we are just transmitting the analogous pulses. Okay, but digital pulses cannot be transmitted because it is actually ideal, right? So we can't generate the pure digital pulses like that. So that's why we can transmit. As the pulses from continuous time signal, first pulses are generated, then from pulses the coding is getting done, and from coding several digital discrete binary codes is generated, and the binary codes is modulating by analogous signal or analog signal. That's why this total process has been named, it is pulse code modulation. Pulse code modulation, that means first pulses are getting generated, that means first sampling is getting done, and from that sampling the quantizing is getting done. That means from the sampling several discrete values has been generated. From sample to quantization, that is pulse code, and after quantizing the values are getting transmitted through the channel by some analog signals. That is called the modulation. That means the total name has been done here, that is pulse code modulation. Okay, I think the quantizer has been clear to you. Okay, and we have also told about the PCM generation. That means our 6 point has been also covered here. Okay, 6 point has also been covered. That is how PCM is getting generated. That means after quantizing, actually what? After quantizing the binary code, that is actually the PCM code. Okay, that is actually the PCM code, and we are just transmitting the PCM code just by some signals, by some analog signals. Okay, nothing more about it. Now we will see the block diagram and operation. Okay, see this block diagram very carefully. This is a PCM block diagram. Okay, this is a PCM block diagram. See each and every block carefully. I will make you understand what block is doing what. See, this is an analog message signal. That is the message, the main message that is getting generated. That is our voice signal. It may be. What is that? It is the analog message signal. It is a normal continuous time signal, right? Normal continuous time signal. LPF, a low pass filter, is given here. Why? Because we know each and every signals in nature, that is analogous. Our voice signal is analogous in nature. Even noise is also analogous in nature. To remove noise, to protect our analog signal from noise, so that the noise can't affect it, we have used a low pass filter, that is noise rejection. As noise is a high frequency signal, we know that the noise is a high frequency signal. So that's why we can say that if we can pass the low frequency signal, that is our voice signal. Our voice actually the low frequency signal. Noise actually attacks the amplitudes, not the frequencies. So the higher frequencies of our voices will be attacked by the noise actually, right? But the lower frequencies will be as it is. So that's why if we can extract the lower frequency signals from our voice, that will not be considered that the noise has been added with it, as the noise is high frequency signal. So that's why noise will be rejected. Okay, then this is the sampler. This is sampler means actually what is getting done here, this signal is converting this signal in the sample and hold circuit. This is actually sample and hold. There is a sample and hold circuit inside it, and this is converting the signal in the sample signal, that is the discrete signal, digital signal, not the digital signal, actually discrete signal, continuous time signal to discrete signal. This quantizer is not nothing but it is the dividing the sample signal in the several levels. Okay, and within that levels, the number of levels is defined by the 2 to the power n. What is the 2 to the power n? 2 to the power n is n হচ্ছে number of quantizer, মানে কত bit how many bits quantizer it have, 9 bit quantizer. Now encoder. What is the encoder? Encoder is just assigning the values to the sampled or the discretized amplitude values. That means from the encoder we can say that our beat pattern is generated, that is 0 0 1 0 1. I am giving a random beat whatever. The beat pattern is generated from this quantized values. From this quantized values means we have fixed the values of the sample signal at some point, because we have to divide the total number of values within the 2 to the power n number of combinations. So that's why you have to discrete the values at some levels, some quantization levels within that 2 to the power n. For our example, there is the 8 number of combinations. Okay, so from that values, encoder is just doing what? From that values, it is assigning some particular codes, because we know that for 3 bit we have the 8 number of 8 combinations. They are the combinations of 8 codes. Let me say each codes, types of codes, different types of codes can be generated, and the quantizer that the encoder is, that I have already told you, it is assigning each and every quantized amplitudes a particular code. Okay, and this is nothing but our PCM. We can say that this is nothing but our PCM, and that is also written over here, that is the PCM out given to the channel. Now you can see these two blocks, that is same block though there, that is the regenerative repeater. What is that? Think in the practical way. Suppose you are transmitting a PCM signal from a transmitter. Now the receiver is far long away from the transmitter. That means the distance between the transmitter and receiver is very very long, right? The distance is very long. So that's why it may be that the signal may be attenuated in the mid of the wave, in the mid of the channel. That means the channel is very long, noise can be affected, or for other parameters of the channels also, the signal may be attenuated, right? So that's why what is happening here, a repeater as a small block that is just regenerating the same pattern. Suppose this pattern is being transmitted, this is the regenerating the same pattern, 0 1 0 1 0 1 1 1 and so on. The same pattern it will regenerate, so that the signal that was just attenuated, that was just the amplitudes of the signal, or the signal that was just being lost, will be regenerated again. And remember that regenerate means nothing but, regenerate doesn't means the amplify actually. Amplifier is completely another thing. Regenerative repeater is just the same beat pulse, it is just generating again. It is not amplifying the previous signal. Amplifier is completely different, right? So it is not amplifying the previous signal, the same beat pattern is generated by this block again. And the two things the two regenerative repeater representing here, that means there may be multiple number of regenerative repeater present depending upon how long, up to how long distance you want to transmit your PCM code. So according to the calculation you need that number of regenerative repeater also. For smaller distance you need a smaller number of repeaters. For larger distance we need larger number of repeaters. And this is the channel output. Now the reverse thing is getting done over here. What is that? From here we have whatever we have got. We have got the digital codes, right? The same digital codes. Okay, 01, 01, 0111 and so on, digital codes we have received. From these digital codes we need to regenerate this sample signals. What is the regeneration circuit is doing? The regenerating circuit is just regenerating the sample signal again. And from this sample signal, as the sample signal is regenerated, just the reverse thing of the quantizer, from whatever the quantizer and encoder was doing, quantizer and encoder was just generating the digital code from the sample signal. Regeneration is nothing but from the digital code the sample signal is generated. For quantizer and encoder, for sample signal the digital code was being generated. So regeneration is nothing but the reverse process. And decoder key, as there was an encoder, decoder is nothing but regeneration and decoder. These two, the combination of these two blocks are generating these signals actually. And this signal is getting then fed to the reconstruction filter. Reconstruction filter just nothing but the constructing the previous continuous value signals that was being transmitted from this sample value signal. From this sample value signal, as it is a filter. So what will be the filter? Filter is just trying to make this signal it a continuous to remove the ripples. Okay, so as this is a filter, the reconstruction filter, this is reconstructing, the name itself suggests this is the reconstructing the same signal that was being transmitted at the sender side. This is the reconstruction filter, just making this discrete or the sample signal to a continuous valued signal. And after all, this is the destination where the signal was generated. Okay, where the signal is to be transmitted, is to be reached. Okay, this is the destination. That may be a loudspeaker or another person or another human receiver also, whatever. So this is the total block. And you can see the upper block, this is this portion. This portion is the transmitter section. That means from here whatever we have done, we are doing actually, why it is called the transmitter, we are just giving an input of continuous time signal and output is digital data, right? So that is, it is called transmitter. And this is called the receiver. Why it is receiver? This is because this is where we are giving input the digital data and we are getting output a continuous time signal. That's why it is called the receiver section. And in between the channel is present, and within this channel several number of regenerative repeater will be present just to regenerate that signal, so that the signal can't be lost, the signal can't be attenuated, and this. Okay, this is the total block diagram of the PCM, how PCM is getting generated. This can be it can be transmitted, and this can be detected by the receiver. Now the last thing that I will show you, that is how the trainer kit looks like and how to measure the PCM in the trainer kit actually. This is very very important because this is the thing that you have to perform in your laboratory. Okay, so this is very very important. Just listen about it. See, In tenor kit, you will find two types of kits. One is transmitter kit and one is receiver kit. That one thing that I must have to mention, that is, as here, as in a practical life, you are transmitting the signal from transmitter to receiver, and the distance between transmitter to receiver is very long. That's why we need a regenerative repeater in our practical life. But in tenor kit, obviously the distance between tenor kit, there are two tenor kits that I have already told you. One is transmitter one is for transmitter or modulator, and one is for receiver for detector. Obviously the distance between tenor to transmitter and receiver will be very less. That's why the regenerative repeater won't be seen. Okay, there is no need actually for regenerative repeater. No need of the regenerative repeater. It is also it is just only need for our practical purpose only, when we are transmitting original PCM signal from far to far receiver from a transmitter, right? Now, how the transmitter blockage look like? Don't be confused after seeing this transmitter blockage. See what we are doing actually in laboratory. Okay, I will show you each and every diagram whatever we will get in laboratory, and how to measure the PCM codes, etc. No need to worry about it. Just whatever I am showing, just look only that points. Okay, this portion is our PCM generator. Okay, PCM generator. If you can see clearly, this print has been hazy. So whatever, their sample and hold amplifier has been written over here. That means these two are actually the signal, the analog signal. Two signals I have used, that is, one is 500 Hz, 500 Hz, and one is 1 kilohertz. The two signals of two different frequencies I have used over here. So just whatever we have done, we just you can just take one signal also. A single signal is enough. I have just whatever I have done, I have just multiplied these two signals just to see that what will be the output if we if we mix two signals. Okay, whatever. So you can take one signals, that is the 500 Hz signals has been connected to this channel, and 1 kilohertz signal has been connected to this channel. So two signal has been connected to two channels, and two channels are nothing but there are two sample and hold circuits over here. So you can use only one also. For only one you can use only one signal also. And this is the our voice signal. You can see in the screen that I am showing the 500 Hz signal will look like this. I have clicked this picture from DSO, how the 500 Hz signal looks like. Okay, and the 1 kilohertz signals looks like this. I think you can also see this picture in the screen. Okay, and I think you can't distinguish these two types of signal, that is the frequency of these two types of signal. But if you look the time period, I think you will be understand what is the higher frequency and what is the lower. Okay, first of all, first whatever I have shown you, that was the higher frequency, that is the lower frequency, and second second sinusoidal waveform was the higher frequency. Now whatever we have to measure, actually this after transmitting these, okay, so after sampling and hold, then quantizer, then encode, there is a small op-amp like structure. This is nothing but quantizer and encoding. After this you will get the PCM codes. At the 4-bit quantizer has been used over here. That's why 4 LEDs has been present here. Because what is this 4 LEDs representing? These 4 LEDs are representing the 4 bits. That means the quantizer present over here, that is nothing but a 4-bit quantizer. So you know, for 4-bit quantizer, how many combinations we can get? We can get 16 number of combinations. Okay, we can get the 16 number of combinations for a 4-bit quantizers. That's why whenever you will run this kit, you will see you will see 16 different status, 16 different combinations of this LED blinking. That means, what are the 16 combinations actually? Digitally, we can say the 16 combination starts from 0000. That is 00000001 0010 0011, and from sequentially from 0000 to 1111 is the 16 combination. But remember that for PCM you won't get these 16 combinations sequentially, because according to the variation of the signal that I have already told you in the notes in the lesson, that is according to the variation of the signal you will get the combinations. So for 16 different combinations you will get the 16 LED status. That means, if I give you an example, the 4 LEDs are blinking, that means 1111. Okay, the 2 LEDs are blinking, 2 LEDs are off, that means 1100. How this can be measured, I will show you through a video. I will show you. No need to worry about it. Okay, but just for now, just focus here. In this way, from 0000 means 4 LEDs are off. Okay, in this way the 4 LEDs will be blinking continuously according to the clock signal. According to when clock is blinking, at each and every blink of the clock, 4 LEDs will change the status. For first clock, 4 LEDs will give one status. For second clock, 4 LEDs will give another status, etc, etc. So it will be more clear to you when I will show you a small video. Okay, and one more thing, two things you also have to measure. That is, this is the transmitter clock, and this clock is that clock. After each and every blink of this clock, you will get different status, different combinations of LED blink here. Okay, according to the combination, which LEDs are blinking, that bits will be 1, and the LEDs which was not blinking, that bits will be taken as 0. Okay, so according to the blinking and according to the combinations of these 4 LEDs, you have to note down the 4 bits continuously, and you have to keep noting down those bits continuously unless or until the same bit patterns are getting generated or repeated again. Okay, that means actually after 16 combinations you will see that the same bit patterns, you have written the 16 number of bits, 16 number of data, 16 number of 4 bits. After written 16 number of 4 bits, you can see that you will be able to see that 16 number of data are repeating again. So you will definitely understand that this is the 16 bits that we are getting for one cycle. That is for one cycle of our input signal. For one cycle, the 16 number of bits we have got. For another cycle, again that 16 number of bits will be got. Okay, if the analog data is sinusoidal or not random data, so then you will get the same 16 number of bit patterns again and again. And you know that we are giving the signal sinusoidal signal, right? Just defined scene frequency. As we are giving the sinusoidal signal, our signal is each and every cycles of the sinusoidal signal is equal to each other. That means the frequency or the harmonics are different, but the each and every cycles are same. So that's why the 16 different codes will be repeated again and again. The same codes will be repeated again and again. But if our input signal is random, just like not the sinusoidal or cosinusoidal, just a random signal, then the continuous, discrete and separate codes will be coming again and again. So this will be very much critical to recognize. And for sinusoidal or cosinusoidal signal, the practical is very much easy. So whatever, this is the transmitter clock, and how this transmitter clock looks like, I am just giving a picture, giving the clip of the picture over the screen. You can look, and this is the transmitter sync. Sync is a signal. You can see the what you know that what is the sync pulse and how the sync pulse looks like. You know it very well. So I am also giving the picture of the sync pulse on the screen. I think you can see it. So this is the transmitter section, and from this transmitter section, the transmitter clock and the transmitter sync, these two things will be connected to the receiver. Basically, transmitter sync, this the sync pulse is sending from transmitter to receiver just to synchronize whatever beats are coming, etc. Just to synchronizing purpose, sync pulse is sent, and the clock is just connected to the receiver because I have just considering a single clock. The same clock has been actually should be connected to the receiver, though the receiver section has different clock. Just I am just for reference just connecting the same clock to each other. Okay, and obviously in practical case the clock of the transmitter section and the clock of the receiver section must be same, but the receiver kit you will find the separate clock signal also, so you can use that clock also, or you can use you can connect these to these. Okay, so you have to measure these two signals, and this is the receiver circuitry you can see, and this is the transmitter clock. This is the receiver clock. Receiver clock is connected to the transmitter clock that I have already shown in the previous picture. Okay, and this is the receiver sync. Receiver sync is the connected to the transmitter sync. See, this is the transmitter sync. This is the transmitter clock. This transmitter clock is connected to the receiver clock, and transmitter sync, that is, this is the transmitter sync. This transmitter sync is connected to the receiver sync. So receiver sync pulse is need not to be measured because the sync pulse is same for transmitter and receiver, but receiver clock should be measured again. Okay, I think receiver clock signal will be seen over the screen. I have shown you, I think, and you can find the similarities. Basically these two signals are same, and the frequencies of these two signals are also same. Okay, now the thing is retrieval of this signal. We have generated PCM, but we haven't demodulated it, and we haven't detected our original signal from our PCM. So how this is done actually? See, this is the demodulator circuit, this portion. In this portion is internally connected to the transmitter circuit, and this is the two lines and which has been connected to the transmitter. But unfortunately our kit is not working, our receiver kit is not working here, but I am just giving you how to measure it. See, from channel 0 you will find the channel 0 of the signal that was connected to the channel 0 of the transmitter side, and from channel 1 you can detect the channel 1 signal that was connected to the transmitter side. That was 1 hours 500 Hz and 1 hour 1 kilohertz. That 1 kilohertz and 500 Hz, that is the 500 Hz are detected from here, and 1 kilohertz will be detected from here. The demodulator circuit that I have already shown you in the block diagram, the working of this circuit is same. Just you can see that there is a RX output has been shown over here. Okay, so that's nothing more about it. Now I will show you how the transmitter, how to measure the transmitter, from transmitter how to measure the PCM codes actually, and up to how much you have to take the code, you have to write the code, and how you have to write the code. These two things I have to show you. Okay, so let us jump to our computer screen, how the video has been created, and how we have measured actually the, how you have to also measure the PCM output. Okay, so let us jump to the computer screen. So you can see here that I have recorded a video. Okay, I have recorded a video during the laboratory. Okay, you have seen that I have already shown you this 500 Hz and 1 kilohertz, these two signals, this is the two signals has been connected to the channel 1 and channel 0. You can connect also a single signal also. Here I have used only the 500 Hz signal. Okay, so 500 Hz, for 500 Hz signal, what are the PCM codes are giving generated will be shown by the status LED. There are 4 LEDs that I have already told you. So from the status LEDs you will be able to find how the beat patterns that are being generated for PCM code, and this is the clock signals. Okay, and for measuring whatever we have to do, you have to just slow the clock. There is a switch, there is a toggle switch. Initially this will be in the fast, and during the waveform measurement this will remain in the fast also. But as our eye can't detect, due to persistence of vision, we can't detect the abrupt change of the clock. Okay, in fast position, if we keep the switch in the fast position, then what will be happen? Actually, we as our eye cannot detect in the abrupt change. That's why we will see that the 4 LEDs are continuously glowing, but the LEDs were not continuously glowing. LEDs are actually changing their status continuously. So for that, to just to see the change, how to change the statuses, we have to keep the clock in slow mode, so that we can observe the change of the status of the LEDs. So I'm just playing the video. So you can see that there's a timer clock, and after each and every blink of the timer clock, the status LEDs are changing continuously. Okay, after each and every blink of the timer clock, status LEDs are changing continuously. You can see. Suppose if I stop here, that is after one blink, you can see this is the code, that is 0 1 1 1. After the second clock, what will be the code? After the second clock, the code is 1 1 0 1, and you have to note down this code continuously. Okay, continuously for 2 minutes. Okay, so basically this video is 2 minutes, and whatever we have done, you can do one thing, that is you can shoot a video for 2 minutes, and up to after continuously noting some values, you will observe, you will recognize that the some values are repeating again and again. Okay, the same values are repeating again and again. When the same values or the same portion, same values will be repeated again and again, then you have to stop the counting and you have to stop the writing also. But according to the changing of the status LED and each and every counting and each and every changing of the clock actually mentioning here the clock. This is the clock actually mentioning what? Clock actually mentioning the first count, second count, third count, fourth count, fifth count, sixth count. This. So after each and every count, what is the status of these LEDs? According to the status of the LEDs, you have to keep writing the codes continuously, very fast. Okay. So what is the code that I have already written, that I am also going to show you? Okay, that is, you can see that these are the codes continuously that I have kept writing over the notebook according to the changing of the LED status. And no need to worry about what are the two lines of codes here. Basically I have taken 2 types of combinations. One is for only for channel 0, that is only for 500 Hz, and one for a second time I have just multiplied the 2 signals, that is 500 Hz and 1 kHz. These 2 signals has been multiplied just to see what are the changes are coming. You can use a single channel just to generate the PCM codes. The left side, these are the single channel code. I am just going to give an overview how these codes are getting repeated again and again. You can see from here to here, it is from 01002 up to 1110. Here to here, the 16 different codes has been generated, and after that continuously 1 on 1 zeros has been generated, and after staying in the 1110 position for some time, you can see the same codes has been started to generating again and again. So one thing that is after that 0111 1011, and after 1101, after this 1101, the same code, that is 0110001110010100, the same code has was started generating again. So that's why this is the total set of data ignoring the same bits. There are say 15 same bits. Ignoring the 15 same bits, you will find there are 16 number of unique data, unique PCM codes that was generated during the practicals through by means of the blinking of the LEDs, of the status LEDs. Okay, so by means of blinking of the status LEDs, the 16 number of codes will be generated. You have just ignored these struct 4-bit codes, that is 1110, and after this the same bit pattern will be repeated. You will understand when the same bit pattern will start repeating again, then you have to stop the kit and you have to stop the recording also, and that's all about it. I hope you have understood this session very clearly, and if you have any doubt you can ask me in the comment section, and please do give your valuable feedback. I think you have enjoyed this total PCM pre-practical session very clearly. Thank you, thanks for watching, have a good day. We will see in the next video. Thank you.